So, good morning, everyone. So now we come to part 2. And today I would like to give you a general overview of magnetic shape memory, what it does, what it's used for, and things. But just before I do that, I just want to sort of remind you what we did yesterday concerning the nickel titanium. We took a piece of wire and we bent it in the austenite state and in the martensite state. When you're in the martensite state, you can move around the twins. When you're in the austenite state, it springs back. You have the superelastic effect. Yeah? The way to quantify these things are usually to do a stress-strain measurement. And a straight strain measurement typically looks something like this. So you have the stress versus the strain over here. And this is a nickel titanium in the austenite state. So what happens is that in the beginning, you have to apply a certain stress to acquire a certain strain, but then to have further strain, you don't really have to change the stress. So this we sort of exemplified with the dentist thing, with the braces, yeah, with the teeth braces things. So, and then if you go further, then you go into the nonlinear regime, and if you just go up, and then you go up to the, I think that's the ultimate tensile stress, and then it breaks. So it goes into plastic deformation, and then it breaks completely. If you go back, then you have the loading plateau and the unloading plateau, and there is typically a certain amount of hysteresis involved in that, but this system goes back to its own state. Now, so this whole thing can be viewed as superelasticity. Now, superelasticity has some other interesting things. You're going from one state to another state. So if you're going from one state to another state, you're changing the entropy. And if you're changing the entropy, then you may be extracting the latent heat of the system, because the first order transition, there's a latent heat in the first order transition. And when you go through this transition, well, that latent heat has to be either to be supplied or to be extracted, depending on in which direction you're going. And nickel titanium has one other interesting aspect, and that is the fact that this thing is a very good elastocaloric material. Now, this is what I wanted to show you yesterday, but the thing didn't work, and so I'm showing it to you now. I think all I have to do is just click on that, and yes, it's working. You may faintly see the numbers here. They're changing. This is about 19.6 degrees centigrade, and now I bent the thing, and the thing goes up to 27 degrees. I don't know whether you can you see it? It's not. So that was 19, it's 20. Now the temperature is going back down again. It's gone down to about 25, and when you release it, now it's gone to below the temperature that we started with. It went down to about 17 degrees, yeah? So you can repeatedly do this. And you use this as a heat pump, okay? Now that's a piece of wire. And you can see that the process, since we're doing it very fast, is almost adiabatic. Well, nearly quasi-adiabatic, not really. And then, so the temperature goes up. And that's a tremendous change in the temperature. And it's a temperature range where you can cool things, air conditioning, yeah? 27 degrees, 17 degrees, and things like that. And today, in our time, actually, the project that we're running in Germany involves elastocaloric effects, and in particular, the elastocaloric effects in nickel titanium. Now, this is very nice. You can bend this back and forth, but it turns out that there are other problems. There are fatigue problems. And at some point, the thing breaks, okay? But people have gone around that problem by adding some third elements like copper and things. Then you have reversibilities that are practically unlimited. So, and there are now works going on trying to building prototype refrigerators on these things. So this is the elastocaloric effect. What I will be talking about later on is the magnetic version of this, which is the magnetocaloric effect. That we'll be doing that mainly tomorrow. So let's go back to the Heusler's and the magnetic shape memory, the shape memory effect. Now, I was talking about the versatility of Heusler's yesterday, and if any of you are working on it or will be working on it, then you will notice that there are many things associated with these systems. The colors are quite different here. They're very different, in fact. This B is red. What are we going to do about this? Okay, I mean, there seems to be a beamer problem. Okay, then I'll have to tell you which color which is. No, I have the colors over here, but the colors aren't kind of different over there. So this blue, A, okay, those are all the atoms up here in this plane and in this plane. Okay, so they're all blue. This B is this, and this. Okay, this is the Heusler. So we have A, B, and C. And this is the L21 structure. And yeah, we'll see if the other ones actually reproduce or not. So here we have Heusler alloys. We have alloys like the ones that I showed you yesterday, the single crystal of copper, zinc, aluminum, copper, nickel, aluminum. These are non-magnetic, and they show the shape memory effect. Not as good as a nickel titanium, perhaps, but they're there. And then we have a series of effects which are called the magnetic field-induced structural modifications. These we get in the magnetic Heuslers, where we have a ferromagnetic martensite structure. And what we find is that what we mean by magnetic field induced is that by applying a magnetic field, you can do two things. You can either move twin boundaries, as we did by applying stress to nickel titanium in the martensite phase. Yeah, we could bend the wire and do all sorts of things when it was in the martensite state. Well, we can do this with a magnetic field in a lot of Heuslers, and this leads to the magnetic shape memory effect. And then we have Heuslers like nickel, manganese, indium, and some others that which we can take from the martensite state into the austenite state by applying a magnetic field. Now in nickel titanium, we did this by warming it. We warmed it, it went up. You can do this here by warming as well, but you can also do this with a magnetic field. So you have another extra dimension that you can use, the magnetic field. You don't only warm it and cool it, but you can also play around with the magnetic field to induce these transitions back and forth. So through that, the Heuslers also have this property showing the magnetocaloric effect. That's the magnetic version of what I just showed you of the elastocaloric effect. If you can take the thing through a transition, then you'll encounter large entropy changes, and due to these entropy changes, you'll see a lot of temperature changes as well. And then there's a lot going on electron spin polarization. That is the case when some of these materials show this so-called half-metallic behavior. Half-metallic behavior means that in your band structure, you have either the spin-up or the, let's say, spin-up has a finite density of states at the Fermi level, whereas a spin-down, there is none, so it conducts in only one direction. If it conducts in only one direction, then it conducts only the given spin direction in that direction, and this is used currently in the development of spintronics. So this is the versatility, and there's another one added to this, which I will probably be talking about on Friday afternoon, and that's the very strongly pinned precipitates of Heusler alloys, giving rise to the so-called shell ferromagnetic effect, but I'll talk about that later on. This is green. Okay, maybe we should try it on my computer the next time after the break. I mean, there's some things with the colors. Because this was green yesterday, wasn't it? No, I mean, okay, well, we'll see what it is later. We can try it anyhow. So anyhow, what did we have yesterday? We had our twin martensite in the martensite state, and then by applying stress to this, that is just bending the wire here and there, we could detwin this. And after detwinning it, that is, detwinning is this, I use it identically with twin boundary mobility or twin boundary motion. And then that is red. And then by heating it back up again, we can go back to the austenite state. Okay, this was our shape memory thing, and we have the various characteristics temperatures down here. So the question is, can we do all this with a magnetic field? Okay? Can we go from the twin state to a detwin state? Okay? From a multivariant state, that is, to a single variant state. And then by applying a magnetic field, would it be possible to take these paths as well? So this is what I will be talking about. Now, Heusler's, how do we come to the Heusler's at all? I mean, how do we come to nickel titanium at all? I mean, that was okay, it was motivated by some military project in the beginning, but it turned out to be very interesting, the nickel titanium thing. The same thing more or less applies for our nickel manganese gallium as well. So here we have nickel 2 manganese gallium. This is a stoichiometric Heusler. And again, we have the nickels sitting in the planes over here, and these other black ones are manganese and then gallium. Now, in the, of course, the Heusler's go back to the beginning of the 20th century, but as neutron diffraction techniques had developed and other magnetization methods, there was a regain of interest in these things, and so there was a vast study on Heusler's going on. And one of these people was Webster at the University of Sheffield, and he did neutron diffraction on anything that he could get a hold of as a Heusler material. So he did all sorts of palladium-based Heuslers, palladium, manganese, copper, nickel, manganese, copper, all sorts of things. And among these were also nickel, manganese, gallium at that time. And it was back in 1968 when they were doing neutron diffraction at Harwell that they came across the fact that the structure at room temperature, or the structure at liquid nitrogen temperature was not the same structure as it was at room temperature. They didn't have liquid helium at that time, of course. I mean, maybe, or it was scarce, so they did everything in nitrogen, but that was enough to see that there was something wrong with the structure. But look at the time. This is 1968. So Webster went back in 1984. That's how many years? That's 16 years? Yeah. 16 years. 16 years later, I guess, we sort of decided to take a look at this thing again. And then it was confirmed that the structure below 202 Kelvin was martensitic. And until then, it was not known at all that these things actually, well, I mean, the copper manganese systems, some of them, but the nickel manganese based systems, that they showed a martensitic transition was not known. So then it took another 12 years for somebody to decide to apply a magnetic field. And so look at this time, this 1968 to 1966, that's a long time, that's 28 years. It took 28 years from the discovery of the martensitic transition, or the fact that it was not this structure at room temperature, until the time that somebody decided to apply a magnetic field. Now this is very interesting because during these years, people started working with thin films, there were spin glasses, there was high temperature superconductivity, there were all sorts of things. And hoisters were out of date. So nobody really cared about them, but it's all lying over there. So, I mean, I had asked someone to work on nickel titanium in Turkey, and the immediate response that I got was, well, can't we work on something more popular? Well, look, we've got this huge project going on this, but it's this thing of being popular or not popular is what you're working on. Anyhow, so in Finland, Ullako, they found these large induced strains. And by large induced strains, we mean about 0.12% at the moment. But 0.12% is also huge. It's a huge change. Yes, it is big compared to what was known as a time of other magnetostrictive materials like terphenol terphenol was the only one that had a large magnetostriction. That was about 0.10%, something like that, but it was in the same order of magnitude. Anyhow, that was quite large. That was quite large at that time. It's much larger now, but okay, we'll come to that. So suddenly, after 1996, there was this tremendous acceleration in research on nickel manganese gallium hoisters to understand what the strains were. So if we want to know what the strains and things like that are associated with the martensitic transition, then we should look at the structure basically. The colors over here, there is a little contrast here, okay? So anyhow, this is the cubic structure, okay? This is the so-called L21, which we just saw. Of course, this is for the 50-25-25 stoichiometric case. The moment I go off stoichiometry, we have the L21, but then we have some disorder in there as well. Now, the martensitic transition in these things, they go from a cubic structure to a tetragonal structure. And as I said, in the martensitic transitions, the local coordination of the atoms have to remain. I mean, they have to be, the local neighborhood has to be the same. So if I have to distort this, what do I do to come to the tetragonal state? Because the other state in this thing is tetragonal. Now, if you look at this, we can visualize a tetragonal crystal structure within this L21 structure. Now, if we look over here, look at these two atoms, those are these two, and then you go to the next unit cell, and then you have these two, and then you have these, And then you can extract a tetragonal, or you can visualize a tetragonal state out of this cubic state. Now if you take this out, and then if you deform it, you can deform it around there, you have the martensitic transition in these things. So independent of color, there's a slightly better slide showing this. So again, we have here the L2 one. That's all the nickel atoms sitting in it. And here, within this L2-1 structure, you can visualize the tetragonal structure that we have over here. And if we bring this out, this is what it looks like. And these are the various directions. Now, if we look at this from the top over here, we have these gray atoms sitting over here. And then a little bit below, we can see these two black atoms. And then we should be able to see these two white atoms over here, okay, when we're looking from the top of these things. So this is the pure L10 state, but in very many cases, we observe modulated structures in these alloys. And how do we visualize the modulation? So basically, everything is tetragonal. So if we look at this and come over here, let's take a look at this cell over here. So this is more or less identical to this. So we have one of these here. But it's a little off. So it goes 1, 2, 3 in this direction and 3 in this direction. And this is known, well, it was known as the 10M. Today it's known as the 5M. Okay? So you go 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5 to be able to repeat this structure over here. So the unit cell is defined, of course, with more numbers of atoms. And you have this modulation. Another modulation that you come across with is the 14M, or better known today as the 7M. I should have written these as 10M and 5M and 7M, actually. And here you find this kind of a modulation. You find this part of the L10, so you go 1, 2, 3, 4, 5, 6, 7, and then you go 7 again, and to get back to the structure that you have over here. Now, it's easier said than done. These are the bases. You have the L10, 5N, 7M. These are the basic structures that you have. But the case is that these 5N, 7M structures are hardly ever perfect. That is, what you get down here is not exactly what you have up here. It's slightly off. So what you have is an incommensuracy, okay? You have your 7M structure, but it does not measure with the lattice spacing itself, okay? And you may have to go to many other unit cells to be able to find that this plane fits with that plane. And this oscillation that you have here in the structure is your modulation vector, and we'll be doing some of this next week in more detail when we play around with GIAN. Then you can see exactly what's going on, actually. For practical purposes right now, we have the 5N and the 7M. It's not necessary to have the details of the modulation vectors at this stage. Now, if we have a martensitic transition in nickel manganese gallium that can be affected by a magnetic field, well, we would like to characterize that, and the way to characterize that is to look at the stress strain curves, first of all, without using any magnetic field or anything, okay? Because this is a martensitic transition, you don't need a magnetic field first. I mean, you can just apply a stress strain, and you should be able to see the basic properties of these things. So just as in nickel titanium that I just showed you a little while ago, here you are in the austenite state. That's described like this. And then you go into the martensite state. And then you have this plateau over here where you remain in the martensite state. So you have your austenite, martensite, and then you come into the nonlinear range over here. And when you remove the stress, then you're back in the plane phase over here. So in the martensite phase. So this dark thing is austenite. When you go up here, you're in a mixture of austenite and martensite. It's transforming, and then you come here, you're in the pure martensite phase, and then you remove the stress, and everything remains in the martensite state. Now, in the case of nickel titanium, what do? It was superelastic, wasn't it? It went up and then it went back down again. But in the martensite state itself, you would get curves like this. It would be in the martensite state, you remove the stress, and then it remains there. It was the wire thing, you know? You just bend around the wire and you get another shape so that the strain is not recoverable over there. So this is martensite. But what happens when you apply a magnetic field to this thing? So if you take this in the martensite state, the interesting thing about nickel, manganese, gallium, that it's ferromagnetic in the martensite state. You apply a magnetic field, and you look at the strain that you induce. In the beginning, there's nothing, and then suddenly, the magnetic field at about 0.5 Tesla starts inducing a strain. So you're making the thing longer or shorter by applying a magnetic field, okay? And then, so you're in a twin state here. With the magnetic field, you're detwinning everything. And then when you come up here, then you have this tremendous strain over here. This is the case. I'm sorry I said this wrong. This is not a detwin state. It is a single variance state. You can remember these twins that they have crystallographic orientations with certain angles to one another, and each one is a variant. It is possible when you cool through the martensitic transition temperature under a certain stress that you get only a single one of these variants. So if you apply a magnetic field to only a single one of these variants, you can rotate these variants in another direction so that you have a strain. And when you remove the magnetic field, then it gets stuck where it is. The strain is there. So you have to apply a stress to bring this thing back to its original state. But you see here that the magnetic fields involved for creating these strains, look here, that's about 10%. This is huge strain. So this would mean 10%. 10% of 100 is 10. So if you have a meter-long stick of this material, if you apply a magnetic field, it's going to be 1 meter and 10 centimeters, and that is huge. Yeah, it's huge. This is, of course, in a single crystal, and it's larger than anything known when it comes to a magnetic field-induced strain. In the single crystals, it was, in the polycrystalline materials, it was 0.1% almost, a little bit more than 0.1%. Here we've gone up to 10%. So what is happening here? What is going on? So when you're applying a magnetic field to a single variant, what's basically happening is that you're changing the colors are, this is getting black as well, but you're moving around the twin boundaries with the magnetic field. Now, how does that come to happen? How can this happen? Normally, if you have a magnetic material, you apply a magnetic field like to iron or something. What you do is you rotate the magnetization, and everything is okay. Nothing happens to the crystal. There's a small amount of magnetostriction in the order of 10 to the minus 6 Here we have in the order of percent. The case here in nickel manganese gallium is that the magnetization is very strongly pinned to the lattice. So any rotation in the magnetization causes, along with it, a rotation of the crystal structure, almost the crystal itself. So I mean, so you're rotating the whole parallelogram here, let's say, along with the moment itself. So there's a very, very high magnetocrystalline anisotropy associated with this. So in a real system, it looks like this. This is a real single crystal. I think it's about half 1 millimeter or something like that. The whole dimension is not very large. And what is happening over here now is that there is a magnetic field which is rotating. So let's say the magnetic field is in this direction. So we're rotating the magnetic field. You know, if you apply a magnetic field and remove the magnetic field, you're going to have a large strain, but when you remove it, it's going to remain there. So you have to rotate the magnetic field to bring it back to its own old position. And this is what is happening over here. So these two lines, this red line and the green line, as it sees, it is meant to be a guide. So these two show the minimum width of the crystal, and from here to here would show the maximum. So you can actually see the crystal pulsating. It's growing large and small. So now let's look at the what is pulsing there, okay? We have a single variant state, okay? Let's go back to single variant state. You sit in the austenite state, you apply a certain, you have a single crystal, and in a particular direction, you squeeze it, you apply a stress, and then you cool it down to below the martensitic transformation temperature. And if you have applied the stress in the proper direction and the proper size, then when you have cooled it down, you have a state of only a single variant, okay? So you don't have, it's only one part of the twins, the whole thing. And I think there are about 16 possible variants or something like that. I'm not sure right now. But so you select only one of them. And after you've done that, you apply a magnetic field. So this gray represents a variant. For simplicity, I did draw here modulated structures. We have a tetragonal structure with a short c-axis and a long a-axis. It looks like this. And then we apply a magnetic field to this. When we apply a magnetic field, what happens is that we start growing these blue parts which have a magnetization along this field direction and this direction. So these blues, they grow at the expense of these grays. And when the field is high enough, then everything is blue, and we end up with another variant. It's still single variant, but it's another single variant. Now the c-axis is a short axis. Okay? So basically, what we are growing in the direction of the magnetic field are components with shorter axes. Yeah? I think I've drawn this, I'm not sure, okay. I should have drawn this the other way around. This should be here and this should be here. So that when we are growing more and more variants of short axis, the sample should be shrinking. But I've drawn this here wrong, so please see this as here and this as here. So if we have if a single variant state with everything along the short axis, and we apply a magnetic field in this direction, then we will be elongating the sample. In any case, this is then the elongation of the sample. I should correct this. I think I'll correct this and then I'll show that again one time. But anyhow, the idea is to grow variants with a magnetic field that have so that one variant is transformed into another variant. And when we look at the strains of this, of course, coming from here to here, what we have is that first initially nothing happens, and then it goes up, and then we're back down here again. So we have what this is known as magnetic shape memory. It's named like this, but the nomenclature is a little bit more different than what we have for nickel titanium, right? Now in nickel titanium, we define the shape memory effect as coming from one state to the other state, so it remembers its high temperature phase. Now this thing, if you deformed it somehow at the low temperature state and brought it back up to high temperature, it would act exactly like nickel titanium. So that's where the name, the shape memory, comes from. Now, elongating these strains, that occurs purely in the martensite phase. Now, we're in the martensite phase. We're not going from a martensite phase to an austenite phase by applying a magnetic field. Okay? But still, we call this the magnetic shape memory effect. So, in nickel titanium, remember yesterday I showed you here the demonstration with the big spring and the stool, and you could see the forces involved in there. I mean, I could really put weight on that, and the wires still would do all the work that it was necessary to be done. What did I put in as energy? We heated the wire with the flame, and that's a tremendous amount of heat. And somehow we use that heat for the transition, and there's a tremendous amount of force involved with it. Now, here we're applying a magnetic field, and we're getting a tremendous strain of 10%. The question is, can we use this strain? Can I put a stool on this, and will it lift up the stool? And the answer is no, because the energy that you're supplying with the magnetic field is nothing compared to what we're supplying with our flame, yeah? It's very, very little. It's very little. So you're not going to get very much work out of this. So if you do this, if you do these kinds of measurements by applying stress, here we have 1 megapascal to 2.5 megapascals of stress, which are applied while we are applying the magnetic field, okay? So let's try to visualize what we're doing here at 1 megapascal. So we start here, we go up, just as we're doing here. And since we've applied a stress, this doesn't go back straight back, but it goes down because our stress, the mechanical stress, forces us to go back to the original single variant state. It's not removing the magnetic field that takes us back. It's the stress that we apply, the bias stress that we apply, while we are going through this loop. Now, if you increase the stress, you see that this goes down very rapidly, and after some time, it won't be there. Okay? So now, so what can we use this for? I mean, we can't use for moving objects and things like that, it appears to be, but it's a tremendous amount of strain, and you can use these for several other things where not very many forces are involved. You can use it for moving around mirrors, you can use it as actuators, and these are the main themes that these things go around with. So now, are there any, if you have any questions in between, please ask, okay? Since these things are magnetic, we should be looking at the magnetic properties of these things. What is happening here? What is unique about nickel, manganese, gallium? If we look at the nickel, manganese, gallium with varying composition, we had the nickel 2 manganese gallium alloy, which is here, the X equals 0, with a martensitic transition temperature around 200 Kelvin here, right? If we change the composition, we can move the transition temperature further and further up or in other direction, depending how we manipulate these things. And what we see here, these have been measured in a magnetic field of 10 Tesla, it's a huge field. And what we see here is that in the austenite state, we have a Curie temperature somewhere, and in the martensite state, the magnetization goes up. Here also, the magnetization goes up in all of these, okay, when we're at 5 Tesla. But when we measure at low fields, from 100 Oersted to 4 kilooersted, you see that the magnetization first hardly ever changes. In fact, it drops a little bit. And then in fact, so that the martensite state has a lower magnetization than the austenite state. And as you go further up in the measuring field, you find that you have a low magnetization here, high magnetization here. And when you go further and further, you have the case when the low temperature phase has a higher magnetization than the high temperature phase, as here. If we look at the difference of the magnetizations here as a function of field, you see that there's initially a huge drop, and then it goes back up again. Now, before I go any further, I will come back and recapitulate this. This is what I want to say on nickel manganese gallium. Of course, gallium is not the only thing. What happens when we put in there indium and tin and things like that, and how the magnetization develops. So to be able to understand the magnetization of nickel manganese gallium, we have to understand the magnetization of the other alloys that I will present after this. So I think this would be a good point if we took a break, so that we'll come back with fresh minds, and then we'll talk about the magnetization in general. Okay? Any questions right now? Yeah.
Just a small one. I was just wondering that can we see a complete hysteresis kind of loop with field and strain?
Yes, I'll be showing that after the coffee break. No, you'll be seeing that. But in the meantime, with the you mean the magnetic field versus strain, yes? A strain versus magnetic field. The best you can get for nickel manganese, you start with a single variance state, you get this, you go down. If you went all the way back here and back here, it won't go down. Okay? Because then reversing the magnetic field is enough. You have to rotate the magnetic field here in the case of nickel manganese gallium. But I'll be showing that in the next things for the other ones. Okay? So now I'm asking everybody. For nickel titanium, when I showed this picture, was this clear? Okay? Any objections? Is there anything that has not been understood concerning detwinning, variance? Okay? So when we talk about martensite variance, you know that we have twinnings, and when we cool everything down from a single crystal state down to below the martensitic transformation temperature, we have twinnings oriented differently along the crystallographic structure, because you can have a twin appearing in one direction and then in another direction and so on. And each of these, the parts of the twins, are called variants. Okay, and we can have something like up to 16 or something like that, a number of variants which can accommodate itself in the crystal structure when we cool things below the martensitic transition temperature. Now, we can prepare single variants. That is, if you have a single crystal, and if you just cool it down, the variants are just going to select themselves randomly. But if you apply a certain stress in one particular direction and you cool it down through the martensitic transformation temperature, you have a chance of getting a single variant. So single variant would be then a single crystal martensitic phase quasi, because all the atoms will be arranged, okay? So what happens? Remember yesterday there was I was talking about the accommodation problem. When you cool the material through the martensitic transition temperature, then you have different orientations of your variants. They're just random because it's very energetically unfavorable to come to a single variant phase all by itself. You have to supply the energy that is required to stabilize a single variant phase, and that you do it by applying your stress, okay, in a particular direction so that they grow only in one direction. Is that okay? So now we have the magnetic version of this thing. It's the same thing. It's a martensitic transition. You don't have to give it a new name. And you can cool it, change the shape, detwin it, and warm it. You'll get back to the same shape. But additionally, what we have about nickel, manganese, gallium is that in the martensitic phase, it is ferromagnetic. It is ferromagnetic in the austenite phase, and it is ferromagnetic in the martensite phase. So you have a chance of doing something with a magnetic field. You don't have that in nickel titanium. It's non-magnetic. And this is what happens. The green is still there. Okay, you cool it down. You can apply a magnetic field like this, and what do you see? You see the pulsating thing. Yeah. So you go from one variant state to the other variant state. You can apply a magnetic field and you can get a strain. And then you can apply a magnetic field to this thing and it will move from one kind of a variant to another kind of a variant. But in nickel, manganese, gallium, we can't do this. It doesn't work, okay? It doesn't work because the low temperature phase has a higher magnetization than the high temperature phase. And if I apply a magnetic field, the phase that the magnetic field is going to stabilize is the state of higher magnetization. And the state of higher magnetization is the martensite state. So this magnetic field will not bring me from here to here. Now the question is, are there systems that will bring us from here to here? We're going to go into that eventually. So let me go further. The structures and the modulations, we'll be going more into the details of these things later on, but I would like to, just for the sake of visibility, it would be good if you really could visualize this. Can you see the L10 coming out of the L21 here? Is that clear? So, and then if we had only this, there would be no problem. We have L10 all over the place. But then these things acquire modulated structures, and these are the 5N and the 7M, which look like this, and this is like this when you look at it from the top. You'll be having all these figures, okay? So you can go back and look at it more carefully and everything. And then, okay, this was the stress-strain part of the deal. And here there's a little mistake which I have to fix before I do anything else with that. So we're going from one variant to another variant, a gray variant to a blue variant. And I've shown here that the sample gets longer. If it gets shorter by delta L, but the change is delta L, and delta L is in the order of about 10% in this case. And instead of watching, if you measure the length change under a magnetic field, you see that you can change the length of the whole thing by about 10%. Can you put in a load? Yes, to a certain extent, but not as in nickel titanium, because the forces that are involved in this case is very little. I had seen one. It was a very interesting demonstration. Sozinov, this person who I refer to once in a while over here, we had a meeting in the Pyrenees in Spain at some time, and it was exactly then when they had grown these single variant crystals. You could take one in your hand and you could pull it. You can pull it and push it, and you can hear it. Yeah? It's a material, it's just going from the martensite state to the austenite state. And using very, very little force. So the amount of work that these things can do is not very much. You have your Zeeman energy. It's the magnetization times the magnetic field, which is not very much as an input energy. So you're not going to get more out than what you put in. So the amount of work that you're going to get out of these materials is not that much at the moment. So let's, when we go to the magnetization, this will become more obvious when I show you the magnetization of the other materials. Nickel, manganese, gallium is funny in the sense that the magnetization at low temperature, when measured in small fields, is smaller in the martensite state than in the austenite state in the beginning. But if you apply the magnetic field higher and higher, it goes the other way around. Okay? Now, I'll come back to this. But first, what I'll do is I'll continue and show you other magnetization data. And when you have seen that, which is easier to grasp, then we'll come back to this and you can understand this better. Now, nickel, manganese, gallium, we said, yes, nickel 2, manganese, gallium. It's one of the very rare Heuslers that undergo martensitic transformation in the stoichiometric composition. That is nickel 50, manganese 25, gallium 25, okay? Normally, such Heuslers are all ferromagnetic and they're all in one phase. If you want to move around the Curie temperature, you can change the composition a little bit. So all these magnetic shape memory effects that you are seeing and observing, you can shift them to room temperature because the stoichiometric compound, nickel 2, manganese, gallium, has a Curie temperature of about 200 Kelvin, and that's not very useful. If you want to use it for actuators, if you want to use something at room temperature, what you do is you can change compositions, move around Curie temperatures. You can dope it with other materials and so on and so forth. And you can bring all these functionalities to practically whatever temperature you want around room temperature. Okay, so now, nickel, manganese, gallium, okay, it shows these effects, everybody works with it and everything, but isn't there anything else? How can we search for alloys that have these such properties and show perhaps also magnetic shape memory effects? Now, one way of dealing with these things is to try to understand what the martensitic transformations, how the martensitic transformations are in various classes of alloys. When you're dealing with various classes of alloys that have martensitic transitions and you want to visualize them or parameterize them somehow so that you can compare their properties, A convenient way of making such plots is to plot the temperature, the martensitic transformation temperature, as a function of what we call the valence electron concentration. Okay? It's a fancy name, but it's very easy. The valence electron concentration, for example, for nickel, manganese, gallium, if we wanted to know what that was. Nickel has 10 valence electrons. You look at the S and D electrons, okay, in the metallic state, and it has 10 electrons. Likewise, manganese has 7 valence electrons, and gallium has 3. So here you consider the the S and D electrons. Those make up the valence electrons, and here they're the S and P electrons. And then what you do is you just take a weighted average. So you have 50%, that's 0.5 times 10, plus 0.25 times 7, again plus 0.25 times 3. You get 7.5 electrons per atom for that particular composition. Now, this is the number of valence electrons. And then you plot them out. You plot the martensitic transformation temperatures for a whole bunch of materials, all on one graph as a function of electron concentration. You don't care about the individual elements. You care about the number of electrons that they carry as valence electrons. And you do see a certain systematic, meaning that, of course, the valence electron concentration is an electronic property of a metal, and there should be some consistencies independent of what the species are. Indeed, what you see here is a line that ranges from about 7 all the way to 8.5. So it's plotted for various nickel, manganese, cobalt, nickel, gallium, cobalt, nickel, and so on and so forth. Okay? There's this lone material out here, which has an electron concentration of 8.5. So that is nickel manganese without anything else, because nickel manganese is tetragonal. And nickel has 10 electrons, manganese has 7, and if you calculate the electron concentration of that, you get 8.5. And then when you start adding gallium, aluminum, or whatever, the electron concentrations start dropping, and the martensitic transformation temperature drops as a function of, drops with decreasing electron concentration. Okay, so this is what we have at hand. So moving around the electron concentration, choosing correct compositions, you can play around with martensitic transition temperatures. By the way, this area over here, this shaded area over here, lies around 200 to 500 Kelvin, which is a technically meaningful area. And if you're looking for technical applications and things like that, then you would stick around to that composition. So the electron per atom, the valence electron composition thing is something quite old. We know it from the Slater-Pauling curve. I don't know whether you've come across this before, but if you've taken a course on some magnetism and things, you've probably come across the concept of band magnetism. Yeah? So you have discrete states in your atoms, and when the atoms come together, they make bands. Okay? And when you look at the electron composition of 3D metals and alloys, ranging from chromium all the way to copper, if you look at the top part of this curve, you see a certain systematic. So what happens is that here you have chromium, manganese, iron, and so on, going up and up. What is happening over here, your band is filling in one direction, okay, and when the band is full, then the Pauli principle tells us that it has to start filling in the opposite direction, okay? And when you look at the various alloys, the magnetic moments of various alloys as a function of composition, you get this universal-like behavior. And you have some deviations from them. Up to a certain composition, you have the body-centered cubic structure, and above that you have the face-centered cubic structure. It's quite interesting that this starts dropping after, when it starts dropping, the face-centered cubic structure is formed. Anyhow, so you get things like this, and these are our Heuslers, our nickel-manganese-based Heuslers. You see, they follow practically this electron concentration dependence of the magnetic moment. They go up here. And then they deviate. They come down here. This part, here everything is ferromagnetic. Here everything is antiferromagnetic. This is nickel-manganese. And you see here, in our nickel-manganese gallium, nickel-manganese indium, nickel-manganese aluminum, whatever you can think of, one end composition is nickel-manganese itself. So all these things, they have to go down here, okay? Now, why they go down and what they do, we'll be coming to that. Now, let's go to some practical things. We want to choose new materials. How do you choose new materials? How do you make new materials? Well, of ternary compounds. In ternary compounds, you can draw phase diagrams like this, okay? So you have manganese, gallium, and nickel, and this is in a plane of a certain constant temperature. If you want the temperature, then you have to go out of the plane as well. So, but what we plot here are the various intermetallic compounds that occur in these materials. So if you look at manganese and gallium, you find here a manganese 3 gallium, which is hexagonal, a manganese 2 gallium, which is tetragonal, and some other compounds. On this side, you find the compounds with nickel and gallium, all sorts of compounds. Here, what you find is various alloys of nickel and manganese, and you find the nickel-manganese compound over here. When you plot the martensitic transition temperatures taken from the literature, sorry, not the temperatures, but the, if you locate the alloys which are martensitic on this graph, you find that all these little points over here, which are scattered around here, they are alloys that transforms martensitically. So now, how do we read these diagrams? Now, let's look at this. Nickel 2, manganese, gallium. How do you locate these things on these diagrams? We have 50% nickel. So 50% nickel is here. It's also here. It's also, yeah, it's here and here. Okay? So this is the 50% nickel line, what we have over here. And then what do we want? We want 25% manganese. So the 25% manganese line, this is 30, so 25 would be here, and that would go down here, okay? So here we would have the 25% line. So the crossing point of the 50 and the 25 will automatically take us to the 25% of the gallium, so you need only actually 2 of these, and you locate your point like this over here. Okay? It takes a little bit of training and a little bit of looking at these things to see where your compositions actually lie. It's tricky sometime in the beginning, but it works. I mean, it's always there. So anyhow, our technically important region was something between 7.4 electrons per atom and 8 electrons per atom from our previous slide. here. This. So we're looking for materials that we can develop that lie here between 7.4 and 8.0. And so there are between these two lines basically. So, and how do you find those lines? So you go from, you look at nickel and manganese. You look for a nickel-manganese alloy that has a composition of 8. You work backwards to it. You get a point over here. And then you look for a nickel-gallium system that also has 8. And you just join these lines and you get it. So what you have over here is intermetallics, and some things over here. Now, since nothing seems to be stable over here, if I were to put a little bit of nickel into these things, then I would join this line over here. I would look at this range over here, okay? So I have a range in this region where it may be possible to put in some nickel. And then I go look over here. I have nickel and gallium, and I have a limit of intermetallics here. So I can draw a line between manganese and this border and this one over here. So I have a range over here. So it seems that the intersecting range between those two around here, these may have some competing structures of some kind, okay? Because one wants to be hexagonal, the other one wants to be FCC. And around here, we find that we observed martensitic transitions. So then what you do is, then you try to select compounds around in this area. Now, if you do this for both nickel-manganese tin and nickel-manganese indium, which are going to be the next candidates that we prepare for magnetic shape memory, we find that this we have over here, okay, this is the 50-50 line, this is the 25-25 line, and this is where nickel-2 manganese tin sits. And here, that's where nickel-2 manganese indium sits. Now, both nickel-2 manganese indium and nickel-2 manganese tin are stable L21 cubic structures. They don't undergo a martensitic transition temperature. The only nickel-manganese-based alloy that undergoes a martensitic transition temperature, martensitic transition, is the nickel-manganese gallium. Okay? So we're sitting here in both of these systems, and we want to go along a line where we may be able to find a martensitic transition in this thing. If the stoichiometric is not martensitic, then which of stoichiometric would perhaps be martensitic? We have here nickel-manganese 50-50. It has an L10 structure. It's tetragonal. And then we have the L21 here, which is cubic. So if we go along this line, we should be transforming from an L10 to some cubic structure. Okay? And in the course of this transformation, it may be that we encounter a martensitic transition. So this is how, looking at these diagrams, this is how we try to select the alloys that we want to study and the ones that we are interested in. So doing this, we do indeed find martensitic transitions in practically anything. Okay? That goes from nickel-manganese to nickel-manganese X, nickel-2 manganese X. What we do is, when we prepare these alloys, we look at the magnetization. We do a zero field-cooled, and field-warming magnetizations. Have you done these before? Have you encountered these before? Or is anyone has, let me ask you like this. How many people have done or dealt with such magnetization measurements? 1, 2, 3. Okay, good. So, okay, some more. I'll go into the details then of how these measurements are performed. So we have a curve that looks like this. Okay, first of all. Now, how do we do the measurements? If we start with a system where we have, where we know it's magnetic at room temperature just by holding a magnet or something like that, how would you run an experiment? How would you run a temperature-dependent experiment? You put it into a magnetometer, change the temperature. But it's not just like that. It's how you put in the sample and how you start your measurements. That makes a lot of difference. So we start out, we take a sample, and then we cool it down without a magnetic field and nothing. And then we start measuring. When we measure, we get a curve. When we start measuring, of course, we have to apply a very small magnetic field to get a signal from our magnetometer. So we apply a magnetic field, we measure upward in temperature, we go above the Curie temperature, and then, without removing the magnetic field, we take the measurements on cooling down. Now, two things can happen. It can follow the curve that you went up, or it can follow a completely different curve. Okay? So, what happens when we have, are you acquainted with spin glasses? Frustration? Okay, then I should talk about frustration just a little bit. Think of a triangle, okay? On a triangle, you have spins. It's an equilateral triangle. You can put ferromagnets in there, right? 3 ferromagnets. Now, try rotating one. So you try to make an antiferromagnet and an equilateral triangle. So if 2 of them agree, what's the third one going to do? If the third one is going to agree with this one, then it has to point up. If it's going to agree with this one, then it has to point down. So what it does is it can't do anything. It gets frustrated. That's why we call this a frustration. And it points in any direction it wants. It requires some configuration. How many of these configurations are there? Maybe infinite. It can be like this, like that, or whatever. So we call this a glass. Okay, it's like a glass. So we call it a spin glass. So now, if I take this funny frustrated state, let's say this funny frustrated state occurs at some particular temperature. And I am above this temperature, and I am cooling this thing down in no magnetic field all the way down to low temperature. Everything gets stuck in a funny frustrated state. I apply a very small magnetic field to measure the magnetization. Yes, I measure a magnetization. As the temperature increases, what is going to happen? This very strongly frustrated state is going to start loosening, and it's going to interact with the magnetic field, so it points more and more in the direction of the magnetic field. So the magnetization is going to start going up, yeah, with increasing temperature, because I have kT, the Boltzmann constant times the temperature, and it's agitating everything. So the external magnetic field is doing better and better work until it gets to a point where you exceed this frustration temperature, and then everything stops dropping again. Now, without removing the field, if I keep the field over there, and if I go below this frustration temperature, what do I do with the frustration? Because I have a magnetic field, it's not random anymore. It's pointing a little bit in the magnetic field direction. It still freezes, of course. It's still frustrated. But the magnetization that I measure is then larger than the magnetization that I measure when I'm on increasing temperature. And this is exactly what you're seeing here. So